So let's look at a prime example of simple harmonic motion, the place every student starts when they first approach simple harmonic motion, the simple pendulum. So a pendulum is a swinging thing attached to a solid surface of some type. So you have some body. We'll call it a point mass in this case because that makes it a simple pendulum instead of a physical pendulum. And we'll say that it's attached to the little swing point there by a massless string, and it swings back and forth. Swings back and forth, right? So it takes this arced path here, roughly that, and that is our x-axis, not linear. It's an arc. And at any given point, like where I've drawn it, you have an angle that's swept, call it theta, and we'll say the length of this pendulum is a is a capital L length. All right. So string, unstretchable, but it does provide a tension force. So this is an ideal model, considers an idealized pendulum for simplicity. That's kind of what a model is. A person on a swing or a wrecking ball can be modeled by a simple pendulum. Grandfather clock, that kind of thing. So first, is the periodic swinging of the simple pendulum, is it simple harmonic motion, or is it something more complex? Is it some other type of more complex periodic motion? So remember, the one requirement for simple harmonic motion is that the restoring force has to be directly proportional to the displacement, right? So for springs, that was the case. Restoring force is equal to Hooke's law, Kx. But is it the case here? So we're going to look at that. So looking at this figure, you can see that the displacement of the swinging pendulum is not a straight line like I mentioned. It's a curved path. And more specifically, because this length is staying the same, and the point that it's attached is staying the same, it's arc length of a circle, and the radius of that circle would be L. So if you remember, arc length is defined as S equals R theta. That's usually the way that you typically see it. In our case, what that would mean, arc length is really our displacement x, right? So it would be x equals radius L. So x equals L theta. So really, instead of confirming that the restoring force is directly proportional to x, we need to look for if it's directly proportional to theta, because that's actually the path here. So is it? So looking at the figure, we can identify some forces. So we have a tension force here, and we have gravity acting downwards. So mg. The tension is always pointing radially inward, but gravity is always pointing down. And so it's not exactly the restoring force of this pendulum. It's kind of sort of, it contains a component that provides the restoring force, but it's changing as the position changes, right? Its direction is changing, not just its magnitude. So we got to take a closer look at this. So really, if we broke this up into components, we have a component here, which is the radial component of gravity, and we have a component here, which is the tangential component of gravity. That might have been drawn a little bit too long. There we go, something closer to that. So, if we notice that this is still the same angle, theta, then this here would be mg cosine theta, and this here would be mg sine theta. Make sure you agree with that. And so, which one of those two is our restoring force? It's the one that's pulling it back towards its original midway position, right? So it's this guy here. So, and this is actually, this would be a negative, right? Because it's pointing in the negative x direction. So, our restoring force, F restoring, is equal to negative mg sine theta. What was our original question? Is the restoring force directly proportional to our displacement? And our displacement in this case is an angular displacement because it's arc length of a circle, so theta. So is our restoring force directly proportional to theta? It might seem so, but it's not, because we have this sine involved. So our restoring force is directly proportional to sine theta. So what are you saying, Joel? That this isn't simple harmonic motion? This idealized model that you brought up specifically for this section isn't simple harmonic motion? Well, there's something called a small angle approximation for sine theta, where for small theta, sine theta is about equal to theta. And you've probably seen this before, but if you haven't, it's used a lot in physics. If you expand sine x into its Maclaurin series, you get that sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So this means that for not very large x, the leading term of sine x is x in this expansion. So if you're willing to sacrifice a tiny bit of accuracy, then you can, and for very small x, you can approximate sine x to x. So this means for our pendulum that if we aren't making it swing very far, if we're not pulling it all the way back, then we can still stay pretty accurate by approximating the restoring force to be proportional to theta instead of sine theta. So if we just have our pendulum and we just swing it a little bit left and right instead of big wide sweeps, right, like a huge wrecking ball, I guess. If we're just looking at little left and right oscillations, it's pretty simple harmonic. So going back, if we rewrite the restoring force for assuming small theta and this small angle approximation, then our restoring force, go back to blue here, is equal to negative mg theta. And we know from arc length that theta is equal to x over L. So that would be negative mg x over L, or just to write it a little bit more obviously, negative mg over L x. So now we have it directly proportional with this proportionality factor here, negative mg over L. So hopefully it makes it clear that this this mg over L is our quote-unquote spring constant. In this case, it's not a spring, but it doesn't have to be a spring. We might more aptly refer to this as a force constant. But it's the same concept. It's the restoring force proportionality constant, and it's equal to mg over L. So with this, we can find our angular frequency, our frequency, and our period. So let's go ahead and do that for our simple pendulum. So we have omega is equal to, from before, k over m. But now we have k that we can plug in. This is k. So that's equal to mg over L over m, which simplifies to g over L. All right, for a simple pendulum. And then our frequency, we said, was omega over 2 pi, which is equal to 1 over 2 pi. And we can plug in our new omega, being g over L. And our period is the inverse of that, 2 pi over omega, which is equal to 2 pi L over g. All right, so are you dissatisfied with our small angle approximation? Does it seem like we're cheating because really this is only valid for if you kind of pull the pendulum back a centimeter or two? Well, I invite you to test how robust this simplification really is. So calculate what the true period would be for if we were saying theta equals 15 degrees, which is a healthy amount to pull back, right? It certainly isn't, full bore, but maybe it's about what we've drawn up here, maybe a little bit less, but it's still it's a good swing, I would say. So using the non-simplified version of period, I'll write this out, and I want you to calculate what it would be for theta equals 15. So 2 pi L over G times 1 plus 1 squared over 2 squared sine squared theta over 2 plus 1 squared times 3 squared over 2 squared times 4 squared sine to the 4th times pi of pi over theta over 2 plus yada yada yada. You can keep going with that. So you can go to as many terms as you want. You see the pattern. And what you should find, what I found, is that the true period, it is longer than the small angle approximation, but it's longer by less than 0.5%. So to me, this is a pretty useful simplification because that's a lot of extra plugging into your calculator that you got to do. So the small angle approximation can be actually really useful. And these simplified models in general, where it may seem like we're neglecting way too much of real-world conditions, ignoring all these things that must be very relevant and change the answer drastically. Well, simplified models can actually be more accurate than you think, and I hope this kind of indicates that to you. All right, that's it.